thanks for inviting me and thanks for the great introduction. I will be mainly focusing on the implicit type of metacognition. Kristen's already elaborated on greatly. Specifically, I'm going to tell you about a project I've been doing in my PhD where we use pupillometry to measure the effect of neuromodulation on this type of implicit performance monitoring or uncertainty estimation. So yeah, very briefly, when you're making decisions in the world, it's useful to have a sense of uncertainty associated with this. It's kind of embedded in the coding of the system. So for example, when you're cycling around on a sunny day, you have a pretty precise estimate of the distance between you and the person in front of you. But if sensory conditions deteriorate, you might have the same mean estimate of this distance, but there's also more uncertainty associated with this. And this example just shows that it's actually useful in guiding adaptive behavior to not only know about this point estimate, but also about the uncertainty that you have. And perhaps, for example, change the riskiness of your behavior. So, yeah, this is all, as I said, kind of implicit. It doesn't really speak directly to whether you have reportable access to this. And if we put this in a bit more formal framework of signal detection theory, how much of you are already very comfortable with signal detection theory? Okay, I'll just do a brief introduction. So let's say that you make one judgment about the state of the world in a certain feature space. So let's say a distance here. At any given trial that you do or action that you make, you have an internal decision variable that, as Chris already said, can be corrupted by noise that's both out there in the world and internal in your brain. So if we would assume that there's one state of the world and we make the same decision over and over again, we would get a kind of distribution of internal samples. And this internal state is called the decision variable. So every time we just have one kind of readout of what the brain thinks is there at that moment. So in the lab, then we often have people compare two different options and make a choice between them. So yeah, we can present them with A or B. And importantly, at every moment, you might know, for example, that you drew this value of the decision variable, but you don't know actually from which of those options it came, which generative distribution underlies this. So the best you can do to make a decision and choose an action is to simply compare the value that you have, say here, to a certain decision bound. So you can, yeah, ideally in this case, you set it in the middle. So in this very simplified case, whenever your internal variable is here on the left, you would answer A. Whenever it's on the right, you would answer B. And of course, in this case, most of the time, if B is the real state of the world, you would be correct, but also sometimes noise would lead you to be on the wrong side of the bound and make an error. Now, in this first case, the stimuli were quite far apart, so there's not so much overlap between the two, but you can make the trial more difficult by putting those two closer together. What you then see is that you're going to be wrong much more often because there's just more overlap, so whenever you draw a sample coming from this distribution, there's a larger chance it's going to sit on the wrong side of the bound. Now, yeah, this is very much used framework for studying decision making, and we can distill a very basic measure of uncertainty or performance monitoring, metacognition, if you will, from it. So if we have at a single trial this sample of internal variable, we can take the distance, or the absolute difference to this bound that we have set there for ourselves, and the distance here is actually a measure of how certain you are about this decision. So the further away, the less chance that you are in this kind of overlap area where you're more likely to be wrong. So here, if you make an error, you don't actually know yet before you receive feedback probably whether it's erroneous or not, but you also have a certain confidence or certain certainty associated with it. In this case, you're going to be much more certain. And so what's interesting about this pattern is that it produces a very specific prediction about the relationship between the intensity of the stimulus and the certainty that we have about it. So if the stimulus is quite weak, so these two distributions are overlapping a lot, you're going to make more errors. But on average, if you can still do the task a bit, you're going to be a little bit more certain on those trials on average where you're correct. So the certainty, if we take this definition, is simply this the whole area there under the curve. So every time you take a sample, you take the distance to the boundary, you sum them all up. So if you're erroneous, you're going to be a bit less certain. If we make the stimulus easier, however, so we pull those two apart, you see that on correct trials, on average, you're also going to be much more certain about it, because the center of mass of this whole distribution is sitting further away from the bound. So on average, on those correct trials, you have more certainty. But for error trials, we see the opposite pattern. So the intuition is here that if the trial is very easy to see, actually you have very strong sensory evidence, but you still make a mistake. There must have been a lot of noise, either external or internal, and because this noise leads you to sit really at the edge of this distribution, you have to be very close to the decision bound. So there has to be very low certainty associated with this decision. Does that make sense? So that's a kind of key prediction here, that we get these diverging slopes. So this was all kind of formalized nicely in this paper by Adam and Kepech. And what I'll be using in the rest of the talk is not this certainty measure, but 1 minus the certainty, so that's the uncertainty, which is easier in the results I'll show you. So remember this. So what do we know about the brain and how it implements this? So when we have a whole network, where in this case, for example, visual information comes in and information is transferred to a parietal-frontal network, and in the end it leads to a motor action. Studies in rats have shown that the orbital frontal cortex actually fires in exactly this predicted pattern. So here it's a little bit different. The difficult trials are in the middle, where there's a 50% mixture between two stimuli, and the easier trials are off to the left and to the right. And we see that those neurons actually fire as predicted by the model. So the easier the trial becomes, so the lower uncertainty, also the lower those neurons fire. And for error trials, we see the opposite pattern. And this similar results have also been found in the monkey, in frontal eye fields, and in the pulvinar. So it seems that there's several regions that either encode or at least have access to the encoding of such an uncertainty estimate. So we know that the orbital frontal cortex projects quite heavily to also brainstem regions that then send these widespread diffuse projections to a lot of cortical areas. And from a theoretical point of view, and also some experimental work has shown that these brainstem areas could be in a perfect position to actually broadcast uncertainty throughout the brain, and indicate the need for changing behavior or learning more at that moment. These neuromodulators, such as noradrenaline or acetylcholine, change the synaptic gain in whole cortical circuits, so they can then drive the change in behavior. And what's interesting is that recent work has shown more and more that these brainstem centers don't only fluctuate over a day, for example, but can also have very cognitively specific responses to specific events. And we can measure their activity using non-invasively the pupil diameter, which is it's easy to measure in humans during all kinds of tasks, and it allows us to infer kind of this neuromodulatory state and the cortical state that the subject is in. So we set out to investigate how much the brainstem knows about such uncertainty computation. So people did a 2-interval decision task where they saw randomly moving dots on the screen. So for seeing those, it's people just fixate in the middle, and you see this whole cloud of dots that are all randomly moving around from frame to frame. So they start with a fixation interval, they hear a short beep, and they see the dots moving in one of the 4 diagonal directions with the 70% motion coherence. So that means that 70% of the dots are moving in the same direction and the rest is just noise. There's a short delay, and they see a second test interval in which coherence is either higher or lower. So they have to then make a judgment afterwards whether their second stimulus was stronger or weaker than the first. We measure their pupil, we wait a little bit to properly capture the signal, and then they get auditory feedback. Lots of people can do this task quite well, and we can define a measure of sensory evidence as the difference here between those two coherence levels. So for example, here at minus 30, the second stimulus would be 30% less coherent than the first, and people would almost always respond that it's weaker. So 27 subjects did this task. So we have these random dot stimuli, and we wanted to investigate the relationship between these trial-by-trial changes in the stimulus and see how it affects behavior and the pupil signal. But one problem with this was supposed to be a movie, but it's stationary. But one problem with these random dot stimuli is that you're actually generating stochastic patterns. So yeah, you have the signal dots that are moving, but you're also adding this noise, which can actually change the real stimulus that is presented to the subject from trial to trial. So it adds this extra noise out there in the world already that you don't know about. So to solve this and to know more about this noise, we did motion filtering, which is very specific to the stimulus. But basically, you save the actual movies that the subject saw in each trial, and you build a filter, pair of filters that is oriented in space and time alongside the direction of motion of the stimulus. So you convolve both of these with this actual stimulus, where and sum them, which leads them to output a position and contrast invariant measure. So it's a bit of technical detail. It's not so important to know exactly how it works, but what's important is that it gives us a frame-by-frame measure of the motion energy in a specific direction that the subject is looking for. So here we see, for example, in this trial, we have a fixation, and in the first interval, the motion strength goes up, and in the second interval, it's even higher. And we can then get a single trial measure of sensory evidence by taking the mean of each of those intervals. So here you see just what that looks like. So for example, take again the 30% weaker stimuli where there's a whole distribution. So here you can actually see on the y-axis, that there's a kind of spread there around each mean. And especially for the more difficult stimuli, they overlap quite a lot. Yes, I'm happy to talk more about this afterwards, but what's important is that we have a single trial measure of the sensory evidence of the subject. So we have these values, and we also have the prediction of the model. So what we found is that even though in this task we didn't explicitly instruct people to change their speed, and also the stimulus duration was fixed, that people adapt their speed basically in a pattern that's exactly predicted by this model. So we see that for correct trials, the easier the stimulus becomes, the faster they are, so the more confident, which is quite intuitive. But when they make an error on a very easy trial, they're actually the slowest. So even though we don't explicitly ask them to rate how confident they are, if we take this proxy of confidence, we can already see that these, there is some monitoring there in the reaction speed, which conforms. This is quite interesting. So some other animal studies and also human studies have actually not found this pattern, which could be due to differences in the task, which I'm happy to talk about. So we know that people, even though they're not explicitly asked to do it, monitor their uncertainty about the task. So we went to look in the pupil signal. So this is the mean pupil dilation. So we have the first interval that's presented. The second one, you see that the pupil already starts to dilate quite strongly. Right. When the two stimuli are presented in rapid succession. And we see this peak right after the response, which is very typical of the pupil signal. So if you've worked with Bold fMRI data, you know that there's this response lag of about 6 seconds, and we see something similar here in a pupil. It's around 900 milliseconds, 1 second. So it's not an instantaneous measure of cortical activity, but it has a certain input response. We wait a little bit for feedback, and when we present the feedback tone, there's again kind of short dilation. So we then wanted to look at what the model predicted about the pupil. So we can split the trials into 3 levels of difficulty, and we see that for correct trials, the easiest have the lowest dilation, so indicating that there would also be the lowest uncertainty associated with this decision. For the error trials, the opposite pattern holds. So you have to look a bit at the color coding. But so here for the easiest error trials, so kind of the most uncertain trials where they make a really stupid mistake, we see the highest pupil dilation. And this effect is really evident right before feedback, but remember that we have about a 1 second delay between actually driving the pupil and measuring it, so probably the cortical drivers or subcortical drivers of these effects should be taking place around formation of the decision. So to test this in a more precise way, rather than just splitting those trials, we used a linear regression, where what you do is on every sample of the pupil, so you have like 100 hertz pupil signal, you actually test the beta weight, so the slope between difficulty of the stimulus and the pupil signal. So basically, yeah, you just do this separately for every sample, and what you then get out is this beta weight, which just indicate how much the pupil signal at that specific moment in time scales with stimulus difficulty. And we do this separately for correct and error trials because we have these predictions that the slopes should be opposite. So this is the ground average, and that's exactly what we see. So already from decision formation, you see this positive beta weight, so the positive slope between stimulus difficulty and the pupil signal, and it kind of dips down here, and you see this opposite pattern of this negative slope for correct trials. So we can do statistics on this, and we took this interval 230 milliseconds before feedback as a kind of reward anticipation pupil response. And if you plot this again, you see that it almost linearly matches these predictions that we have about uncertainty coding. And importantly here, because reaction time also shows a similar pattern, and because a longer decision might also drive the pupil longer, we were a little bit afraid that it could also be an artifact of just having a longer decision, so a longer input to the pupil. But here we also added reaction time on a single trial basis to this design matrix to make sure that we're catching an effect over and above what's already indicated by the reaction time. And across the group, this is highly robust. Any questions so far? So we then asked, is this actually a useful signal for the observer to know? Does the pupil, does it matter actually to behavior? And we plotted the size of the pupil in 100 minutes per subject against the probability that they would be receiving a correct feedback right afterwards. See that there's this nice linear relationship. So here, the higher the pupil actually is, the less chance that they will receive a correct feedback. So here, the more uncertain also indicates that you're more likely to be receiving an error feedback. And we can statistically test this by using a logistic regression where we try to predict the error on every single trial. Some information that we have, so you see that there's a significant positive intercept indicating that they're more often correct than wrong. Of course, the difficulty has a large effect, and then both reaction time and the pupil actually have a negative effect, indicating that the higher this uncertainty that we can measure in reaction time and then over and above RT in the pupil predicts the chance of being correct. So this was also found in the rat, where if they looked at these orbital frontal firing rates, it actually predicted almost from 100 to 50% the chance of receiving a reward. And here we span a much smaller range, so we can't say 100% sure that for the lowest pupil signals they will for sure receive a reward, which is very probably just that there is a lot more noise in the pupil signal from the cortical generators where you're directly measuring the brain to this output that we measure with the eye tracker. So as an interim conclusion, reaction times follow an uncertainty pattern that's exactly predicted by a signal detection theory model without having to ask people for a confidence report. So even though they are not really asking for it, seem to be continuously monitoring their uncertainty. And pupil responses in a feedback reward anticipation period reflect this internal measure of uncertainty. They also predict the probability for warning feedback. So we were then thinking, does the system actually use this uncertainty signal? So in previous studies, people have used experiments where they showed that a higher uncertainty signal makes the subject more likely to opt out of the trial. So to say, for example, I don't want to do this, I'm too uncertain, but we didn't have this here. And instead we investigated a form of response bias, which is a kind of history effect, where we can see how likely people are to either stay with their choices, so repeat a choice, or to alternate to the other option, so between A and B. So we of course randomized alternations versus switches, so whether they had to press left or right on every trial. And here one half would be an exactly equal probability if you just had A to get A or B again. And so in the stimulus, because of the random nature, there's a slight deviation from this exact switching likelihood. But more importantly, in their response, people are much more likely stay, to repeat their response. So they kind of do streaks of the same response, even though in the stimulus, yeah, they should be alternating. So they have this kind of staying bias. And we then again tested if the pupil on the last trial, so if a higher uncertainty before leads them to change this bias and to behave in a different way. So here again we have this logistic regression, which is a bit hard to see because the current stimulus has, of course, the largest effect on what they will do. So to make it easier to look at these coefficients, just plot it without it, and we see that people overall have a bias to stay, but a higher uncertainty, so we can first test whether there's just an effect on the difficulty of the last trial, then the RT, and then the pupil still has a significant predictive effect on the chance that they will switch to a different response on the next trial. So they kind of are more likely to overcome their bias of repeating responses. And you can see what this looks like, and it's a lot more noisy because we're also looking at something like 5 seconds already in the future. But we see that for the highest pupil responses on the last trial, people are more likely to approach this switching rate indicated by the stimulus and overcome this bias. So to conclude, pupil-linked uncertainty prompts observers to act against their response bias and to switch choices from one trial to the next, indicating that they could be less sensitive to kind of history effects that carry over from previous trials. In signal detection theory and other models of decision making, we often assume that trials are temporally independent, that every trial you start again from a kind of blank slate, which most of the time is not the case, and people have significant expectations that the world is correlated in time. So you see that back in their behavior. And so a bit more speculative, neuromodulatory uncertainty signals might be also anatomically in a great place to convey the need for learning and to drive synaptic plasticity. So when you're more uncertain, that could also make you more sensitive to incoming information. So some open questions about this is which neurotransmitters exactly drive the pupil, so which of those brainstem centers are most highly correlated there. We're doing some ongoing pharmacological work in the lab and also brainstem MRI to see which of those nuclei there most significantly contribute to the pupil signal, and also whether individual differences in these pupil responses can account for individual differences in perceptual improvements over time. So if this also actually has an effect on learning behavior. So thanks to my advisor, Tobias Donner, and to OJ Medina, who helped with the data collection. Thanks to the lab, and thanks to you for your attention.
All right, thank you. Any comments or questions? Yes, Mike?
I have really cool studies. I was just thinking, something you could look at. One of my colleagues, Aaron Elder, he's got this really nice paper on whole brain gain. You probably know this.
Yeah.
And he has a very simple measure of, it's the time from baseline to peak in the pupil. And he's shown that it's very related to like the strength of global functional connectivity and individual differences in perceptual decision making. So it might really nicely relate to your in your T-1 type manipulation there. Exactly, to see if, sort of pre-trial whole brain gain, or even from the previous trials, then predicting some of that bias you see would be very cool.
Yeah, I did some things on seeing to what extent the effect of these carries kind of through the baseline pupil. Yeah, it's always a little bit tricky to look really at the baseline in itself because you don't have an absolute measure of the pupil size because it depends a bit on how you exactly measure it, but overall you have to kind of z-score it or so.
Okay.
But it's interesting to think about whether these neuromodulators might be kind of still elevated in the baseline from the last trial.
Right.
And then behavior there.
Yeah, because of course the baseline pupil and the evoked pupil response have sort of alternating mechanisms, right?
Yeah, so they're strongly negatively correlated in most people. We have a few subjects in the lab, we're still trying to get them back who show a positive correlation, but most, I would say like 80 or 90% of people have a trial by trial negative correlation, something like only 8 quite strong.
Right.
So it was really interesting, Anna, really nice data. I just had a question about the logic of interpreting the reaction time as a confidence measure. So I was trying to think about the relationship to the story from Mike Shadland's group and Ruth Becchiani about how they need to add time into their models to get a nice fit to confidence. Right? So, to what extent your data is that pattern, that X pattern, does that fall out of a diffusion model? If you were to simulate a diffusion model and plot the RT as a function of correct and error, would that fall out of that model, or would you then have to add a bit more in to get that fit? And if you did have to add a bit more in, then that would kind of add weight to your argument that that's a proxy for confidence rather than just falling out of an accumulation.
Yeah, so I know that in the 2008 paper they also, I mean, probably for some of the KPH people here, they also get the same effect from a race model. It falls out of that, but I know from the Chiani simulations that it depends on whether you add the elapsed time into the race model as a function of confidence. And so in the latest Chiani work, they actually say they don't get these opposite slopes. So they get the same slope for error and correct trials, as a function of confidence. So it's quite sensitive to the exact model specifications that you use. But of course, it's interesting to think that with something like pupil or like some recordings, you can have a slightly more accurate measure of the internal state. But for the diffusion model, I think you can get it, but it depends a lot on exactly how you specify the model.
So I guess it's difficult to kind of draw a strong link to confidence.
Yeah.
Right, because then
So
it could be epiphenomenal of the way it could be a function of the stimulus strength and the accuracy of the response, as opposed to be linked to.
Yeah. So we can't say anything about like explicit confidence measures, but there is some implicit. So I like the term, I guess, performance monitoring. So the system is kind of continuously monitoring its own uncertainty from trial to trial. But in this experiment, it's totally unclear whether there would be conscious access to this, and because we don't have any report. So, I can't say anything about it. But also, with the rat studies, we can debate whether rats would have conscious access to this, but clearly they are using this type of information. So, it's also useful, even if you don't really know about it, to have this built in your system.
Just something related to that, I think it's also a little bit sensitive to type of reaction time measurement that people are doing in animals, if they also consider the time that animal actually spending to sample the stimulus versus the time that actually animal is actually performing the movement. So separating the sort of response time to two components, one of them being stimulus sampling time and another being the reaction time. In one of the rat databases, I saw better evidence for sort of dependence on a stimulus contrast or in the sampling duration, like the odor sampling duration, but not the movement time. But in the monkey database, I saw a pattern which was kind of other way around, and it was more showing the sort of real reaction time.
I think it also really depends on the task. So some of the experiments, they have actually a reaction time task where the longer you take, the more information you get.
Right.
So that also changes the whole dynamic of like what you're integrating, and you could perhaps then more often adjust, make like a change of mind.
Yep.
Whereas here that might be a bit more difficult because the stimulus. So there's
But I think so one difference with the Chiani work and some of this is that, so here you have this variable that's corrupted by noise. So you get wider distributions, you get stronger signals, which seems a bit counterintuitive. Whereas their model works in this posterior probability space, where you probably take that noise into account. So if you have wider distributions, you would not be more confident if you compute some probability correct, I think. Whereas if you just take the raw signal, you would.
I think in their model they have this, they get the X pattern like you were saying, and if they have more of a race-like architecture, but they don't get the X pattern if they have just a diffusion-like architecture.
Yeah, I know. It's marvellous data, and very interesting that you can get access to these internal states. But I was wondering, and obviously it would be very nice if one could take this into patients. And I was wondering how practical this was, because I noticed in passing that you had 3,000 trials.
Yeah, I mean, so you can do this kind of stuff with fewer trials. So in this case, it was also partly to look at long-term fluctuations in performance, which is not in here now. Yeah, I mean, it is a noisy signal. I mean, clearly, so you need to make sure that there's no light changes already in patients that might be, I mean, yeah, the pupil, of course, reflects much more strongly to light than to anything else. But I mean, I would say in terms of number of trials, it might be comparable to something like EEG, or if you have like 100 or so. It's okay. So.
Well, I guess there's been a lot of research in many years about how to interpret pupil dilation. What does it mean? Someone says it means hiding arousal. Someone says it's a sign of regret. Someone says it's cognitive processing. Someone says it's error, prediction error signal of some sort. And now you say it's uncertainty. So I wonder if you could relate your findings to these kind of other I guess guesses that are out there right now about how to interpret pupil dilation. I mean, or could you, for instance, interpret your results in a different fashion than just uncertainty?
Yeah, I think that the transient pupil dilation and arousal link is quite strong, and it's also a little bit sometimes how you exactly phrase it. So I mean, if you have such an uncertainty signal, of course, for the organism, having a higher uncertainty could also just be more arousing. From one trial to the next. There's this adaptive gain hypothesis that, like, you know, depending on where you are on this arousal curve, you're going to be behaving more or less optimally. So I think, this uncertainty you can kind of fit in there. That if you're on the lower end of the curve, you might need this kind of boost in arousal in your pupil dilation to be behaving more optimally later. So I think it's a little bit also how you call it.
All right, let's, if you have further questions, please write them down and save them for the discussion session, right? But for now, let's give Anna a hand, and then we'll take 5 minutes. Meet back in 5.